Hello everyone, and thank you for joining today's session on Modeling for Seismic Analysis in STAAD.Pro CONNECT Edition. Myself Surajit Ghosh, I am a senior structural engineer and I have been working in Bentley Systems for more than 10 years. Today, I am going to discuss about the basic of seismic analysis and modeling of structures for seismic analysis. I will cover the static seismic part only. I will discuss about different international codes which are available for static seismic analysis in STAAD, a brief discussion on the newly implemented IBC 2018 code, and different options and parameters that need to be specified for the static seismic analysis. Then I will cover the mass and stiffness modeling, how to define the seismic mass for more effectively both for static and dynamic analysis, different types of diaphragms and their effects on the seismic behavior, and finally, how to model the diaphragms and shear walls easily using the advanced options available in STAAD.Pro CONNECT Edition. Before going into the details about the structural modeling for seismic load and application of load, let's talk about the basic of seismic analysis. On the surface, the seismic waves are termed as surface waves, and these surface waves cause the ground to move in various directions and in different pattern. There are mainly two types of surface waves: love waves, where the ground moves in the side-to-side direction, and relay waves, where the ground moves up and down and side to side in the same direction that the wave is moving. These surface waves are the main reason for the ground shaking during earthquake. Now, if the ground moves rapidly back and forth, the foundations of the building attached to the surface of earth are forced to follow these movements. Due to inertia force, the superstructure of any building or the portion which is over the ground remains idle. Thus, the developed inertia forces causes strong vibration of the structure with resonance between the structure and the ground. So, when the ground moves due to earthquake, the overall building structure is subjected to some lateral force that we call seismic force. We can represent this as time versus ground acceleration, displacement. That's why seismic analysis is purely a dynamic analysis. At different time interval, structure will experience different force due to variable ground acceleration. For simplicity of calculation, we modify this dynamic loading into static loading. There are several conditions mentioned in relevant codes like ASCE 7, EC 8 or IS 1893 code when to use static seismic load or when to consider the seismic load as dynamic load. I'll discuss about this later. Instead, there are three different approaches to generate seismic load. First one is the static seismic load or equivalent lateral force method, for which we need to specify the seismic parameters. These are used to calculate the seismic response coefficient and the base shear value. This will be covered in today's session. Second one is the response spectrum method, where we need to specify the time versus acceleration or displacement value. These values are either code specific, depends on the seismic code that is used, or site specific custom data can also be provided. If you know the past earthquake data of your project site, you can easily use that custom earthquake data for the seismic analysis. There are several other inputs which are required, like the damping, scale factor, whether you want to consider the torsion, and signed responses values. This is a dynamic analysis where response quantities for each mode is computed and modal combination method like CQC or SRSS method is used to calculate the final response quantity. And finally, we have time history method, which is also a dynamic analysis but more advanced than the response spectrum method, where we can specify the time versus acceleration or force values. This can be site-specified earthquake data. You can enter it manually or read it from external file, from eqdata.txt file. Time step, arrival time and modal damping values can also be specified, and finally apply the load as ground motion load on the structure. Dynamic analysis will be covered in details in the upcoming webinars. Now, if you look at the basic equation of any multi-degrees of freedom system subjected to lateral ground motion, it looks something like this. Here, M is the mass matrix, C is the damping coefficient matrix, and K is the stiffness matrix. YG component represents the ground acceleration due to earthquake. For any dynamic analysis, the basic equation is followed. So the force that is generated due to ground acceleration depends on three things: mass of the structure, the damping value, and also on the stiffness of the structure. Hence, we need to properly model the mass, damping, and stiffness so that the effect on structure due to seismic force can be minimized. For example, we know that steel structure responds well when subjected to seismic force rather than the concrete structure due to less overall weight of the structure. So reduced mass generate less amount of lateral force. Also, steel material has more ductility than concrete, and we all know that the more ductile material is preferable to resist the seismic force. There are several other factors which I will discuss later. So it is very important to model any structure properly so that effect of seismic forces can be minimized or distributed properly using the lateral force resisting system. First, let's talk about the static seismic analysis and how we can define it in STAAD. As I was mentioning, seismic analysis is a dynamic analysis, and if you want to consider it properly for analysis, then you should apply seismic load as dynamic load. For any dynamic analysis, response quantities for each mode is computed, and these responses are combined together using any method like CQC or SRSS to get the final design value. Here, for each mode, time period and mass participation factors are calculated, and on basis of that, spectral acceleration values are selected. Now, to eliminate the complexity, an approximate method is suggested in different international code, which is the equivalent lateral force method, or what we normally called as static seismic analysis. For this approach, we are not concerned about different mode and behavior of structure for each mode. Here the contribution of the fundamental mode is only considered, and on basis of that, the base shear value is calculated. There are some empirical formula mentioned in each code which are more or less similar. Today, I will discuss only on ASCE 716 code. Eurocode is not available for static analysis in STAAD, so I am not going to discuss this. Indian code is another major code which is followed by large number of users. For ASCE 716 code, seismic base shear is calculated in section 12.8, where seismic response coefficient is multiplied with seismic weight. This seismic response coefficient is further computed from this equation, where the effect of spectral acceleration, response modification factor, and importance factor is used. There are few sub-rules how to compute these values. The spectral acceleration used in this formula is calculated from the design response spectrum curve, which is an average curve of time period versus spectral acceleration, considering the same curve of different zone in a region. Now, to compute the spectral acceleration or SA value, time period is required, which is mentioned under clause 12.8.2. The fundamental time period is considered only for static seismic analysis, and this is calculated using some empirical formula which depends on structure type. For different structure type, different formula and values are specified. Finally, the base shear value is distributed in different story using vertical distribution formula. Here also you can notice that induced seismic force in each story depends on the mass of that story. So mass modeling plays a very vital role in seismic analysis. Let's find the options in STAAD. How to define all this using seismic definition. In STAAD, static seismic analysis is a two-step approach. First, we need to define the seismic parameters and then apply the load from a direction. In the seismic definition window, there are several design codes present. We have Canadian code, Colombian code. Several versions of IBC code is implemented starting from IBC 2000 to latest IBC 2018 version. We have also multiple versions of Indian Seismic Design Code or IS 1893 code, including the latest 2016 version. 3 versions of UBC code is also available. I am going to select IBC 2018 or ASCE 716 code and discuss how to define the parameters. For this code, there are few inputs which you need to specify to properly calculate the seismic coefficient values. In chapter 22 of ASCE 716 code, seismic ground motion and risk coefficient maps are plotted, which are prepared by the United States Geological Survey in collaboration with FEMA and ASCE. From these maps, for different latitude and longitude, you can get the SS and S1 values, which are the risk targeted maximum considered earthquake ground motion parameter for 0.2s and 1s spectral acceleration. Now, if you specify the zip code of your project location, STAAD automatically finds out the latitude and longitude values and then the SS and S1 parameters from dynamic data provided by the USGS. For this, you need an active internet connection as program connects with the USGS site to get the SS and S1 data. If net connection is not present, then you will notice a warning message. In such case, you need to manually calculate the SS and S1 parameters and provide it in the fields. So either you can provide only zip code or provide the SS and S1 parameter values. These SS and S1 values are used to calculate the spectral acceleration values using these formulas. Here you can find that FA and FV values are dependent on site class, which can be specified using site class input. A to F site class is present in the dropdown. Also, you can directly specify the FA and FV values, which will override the site class specific values. TL is used to define long period transition period, which is used to calculate the spectral acceleration value. I is the importance factor, which needs to be calculated manually from table 1.5.1 and 1.5.2. Rx and Rz are the response reduction factors, which is used to calculate the seismic response coefficient value. You can get the same in table 12.21 depending on different seismic force resisting system. Now, the fundamental time period is calculated using the empirical formula mentioned in 12.8.2.1 based on the CT value, height of the structure and X value. These CT and X values are mentioned in table 12.82 depending on the structure type. You can manually provide this as inputs in these fields, both for X and Z direction. If you left these inputs blank, then program computes the average value of the modulus of elasticity of the model from which the CT and X values are calculated. So either you can provide the value or left it blank and program calculates it automatically. Note that for eccentrically braced frames, program is unable to auto-calculate the CT and X value. Hence, if there is any eccentrically braced frame present in your model, you need to manually input the CT and X values. And finally, if you want to override the time period, you can provide Px and Pz parameters. For example, you can calculate the fundamental time period using Rayleigh or eigenvalue methods. You can define the Rayleigh frequency or modal calculation requested command, and once the analysis is performed, you can get the fundamental time period for your model. That value can be used directly as Px and Pz parameter. In this process, you can eliminate the approximate time period calculated from the empirical formula and use more accurate time period calculated from eigensolution method. Now, this seismic response coefficient is multiplied with seismic weight of the structure to calculate the base shear value. Also, story weight is used to calculate the vertical distribution of seismic load. So, mass modeling is very important for any seismic analysis. Coming to the seismic weight definition, in STAAD, the weight required for seismic analysis is defined as a load. So you can simply apply the gravity load and inform the program that these loads will be used for the seismic analysis. Now program internally converts this to weight by dividing the load value with G value. STAAD works with the lumped mass principle. means whatever load you have applied on your structure as seismic weight, during analysis, that load is converted into lumped mass. So if you apply a distributed load, like a member load or a self-weight of member, the overall force is calculated and that force is lumped into end nodes of a member, plate or solid element. Similarly, if you apply a concentrated load or patch load in any intermediate portion, that load is also converted to lumped mass and applied at the end nodes. After converting this mass to weight that is used in the seismic analysis, so you have the flexibility to apply earlier seismic weight as a load, and rest of the conversion is done internally. There are few methods available in STAAD to define the seismic mass. First one is the traditional approach that has been used for a long time, and most of our users use this approach to define the seismic weight. For static seismic load, under the seismic definition, you can find the option to define the seismic weight. You can simply use these options to define the total seismic weight that should be considered to calculate the base shear value. If you perform dynamic analysis, then this seismic weight defined under definition window will not be used. For dynamic load, you need to define the seismic mass in all three orthogonal directions. You need to define the mass model under the first primary load case, where you have included the response spectra or time history load. For any subsequent dynamic load case, same mass model is used. No need to define it again and again for other dynamic load case. There is another method available using which we can define the seismic mass both for static and dynamic load using mass reference load case. This is more advanced than the traditional method and saves lot of time and work. Let's discuss all the options in a STAAD model. This is a G+10 story building which I want to use to discuss how to define the seismic weight using various methods. For this model, I have already defined the seismic parameters as per IBC 2018 code. Also, dead and live load cases are already defined along with other loads. Normally, under seismic weight, gravity loads are included, and in almost all cases, full dead load is considered in seismic weight along with partial live load. Live load percentage depends on relevant code. In few codes, it is mentioned not to consider live load. In few codes, live load reduction factors are specified depending on the floor height. So depending on the code that you are using, you need to add the reduced live load in seismic weight. Though the dead and live load cases are defined under primary load case, still using traditional approach, you cannot reuse them to define seismic weight. First, you need to go to the seismic definition window, and here you can find several options to specify the seismic weight. You need to once again assign all those loads. For example, here you can find that the dead load case contains UDL, which is for external and internal wall load, self weight of members, along with the self weight and floor finish load. Now you need to assign seismic weight by defining all the gravity loads applied in this model. To specify external wall weight, select member weight, then loading type in uniform, specify the weight as a positive number, and finally assign this to all those relevant members. This step needs lots of time. Probably you need to isolate the members from primary load case and then assign. So for a large model, it is a time-consuming task. It is also not possible to directly copy-paste the items using input editor from primary load case, as the load syntax are different. See the UDL loading? In the input editor, you can easily notice that the syntax is different from the primary load item for the seismic definition of loading or the seismic weight, and hence after copy paste you need to manually rectify the syntax. This is also not a good option. Now consider you want to perform response spectra analysis for this model. I have included two response spectra load in X and Z direction using IBC 2018 code with proper input like the zip code, direction factor, site class. What are the functionality of each parameter in this window This will be discussed in the next session. Any dynamic analysis requires mass model where we need to define the seismic weight in three directions as we are concerned about the results of different modes. Seismic weight that is defined under the seismic definition or the static seismic window cannot be used for this purpose. So under the response spectral load case, you need to define all the seismic weights again in three directions. This time, you can take help of input editor. Open the input editor. Copy the dead load items from primary dead load case, say the first three load item, and paste the load values 3 times under first dynamic load case and modify the load direction from Y to X and Z for the rest of the 2 items so that the mass model is formed in both X, Y and Z direction. There you go. The mass model is now ready. Also note that it is better to change the load sign from minus to plus as this is only the weight. I have done this for few load items. Now consider to do the same with all the load items from dead load and live load cases. Well, this is a duplication of job, right? You need to define gravity loads under primary load case, then once again define that as seismic weight for the static seismic analysis, and finally define the same load in three direction for mass modeling for dynamic analysis. Same load is defined thrice, which is not at all user friendly. To make this simple, an option is introduced which is called mass reference load. In the load definition window, you can find one load item called reference load case. This reference load case is not an actual load and does not take part in the analysis. Rather, this is a dummy load which can be pulled in the analysis as per requirement. So you can create a reference load and either use this in any primary load case or in combination. When you define a primary load in your model, that load is not realistic. A seismic load or wind load cannot act on a structure without any gravity load. These primary loads are used to create the combination and we are concerned only with the combination load results. But program always perform analysis for all isolated primary load cases, which eventually increase the analysis time. Now consider a case where dead, live and seismic loads are combined together. For this load, program first perform analysis for dead load, then for live load, and then once again combine all the loads together and perform iterative analysis. This is completely unnecessary as we are not concerned with the isolated dead and live load results. But program don't understand that and hence analysis is performed which increase the analysis time. To eliminate this, you can define the dead and live load case under reference load case and create a repeat load where you can call this to dead and live reference load case and combine this with the seismic load. As mentioned, program does not perform analysis for reference load and hence for repeat load case only, analysis is performed. This is one of the benefits of reference load where we can eliminate the primary load cases and the analysis time required to analyze that primary load cases. Another major benefit is during seismic weight definition. If you create a new reference load case, you can find several load types are present there like dead, live, and along with that there is a specific load type called mass. If you create a reference load case with load type mass, program use this load case for seismic weight calculation. That means you can define your seismic weights under this mass reference load case. For static seismic analysis only gravity loads and for dynamic load case mass in 3 direction. You don't need to define seismic weight anywhere else. So you can simply define the seismic parameters for static seismic analysis and response spectral load for dynamic load. No seismic weight or mass model under response spectral load case is required. Program will read the relevant seismic data directly from the mass reference load case and use it for static or dynamic analysis. No need to define same load data thrice. Just create a mass reference load and specify all your gravity loads there to be considered for seismic weight. It is very easy to open the input editor, copy the loads from dead and live load cases, Say I am going to copy the first 3 load items from dead load case and paste it directly under the mass reference load case without changing the syntax or sign. Program automatically understands that these are seismic weight and accordingly convert and lump all the masses. If you perform dynamic analysis, repeat this another 2 times and this time change the direction from Y to X and Z so that my mass model is formed in all 3 directions. That's all. Nothing else is required. It is very easy, right? No need to define all those gravity loads again and again from the GUI or changing the syntax from the editor. This mass reference load eliminates everything. Simply create a mass reference load and define the seismic weight directly under this mass reference load case and perform your static or dynamic analysis just by defining the seismic parameters. Now you can say, here also we need to copy and paste the loads and change the directions. What if I say this can be automated? Check this model where I have defined all loads. Load 3 and 4 are dead and live loads. 7 and 8 are response spectra loads and rest are other primary and combination loads. I have already defined the seismic definition and response spectra loads. There is no seismic weight added till now, no reference case, no weight under definition. I have created a macro which can auto-generate the mass reference load case. This will fetch the loads from primary dead and live load cases and depending on the inputs, create a mass reference load case. If I click on this tab, it generates the mass model under a new reference load case. And once it is completed, I can simply open the model and check the load definition. See this mass reference load case? All gravity loads are added here in all 3 directions, which will be used in dynamic analysis. No need to copy paste and change the sign or direction. Only create the primary load cases and use this type of macro to auto-generate the mass reference load case for seismic analysis. It is very easy, right? For any seismic analysis, simply define the seismic parameters or response spectra load and use this type of macro to auto-generate the seismic weight. Inclusion of mass reference load is a great feature which helps user to quickly define the seismic weight. There are few things which you should remember during seismic mass addition. For static seismic load, if you specify mass reference load case along with seismic weight under definition window, then program considers the seismic weight only from seismic definition. Mass reference load case is not used and a note is reported in the output file. Similarly for dynamic load, if mass model is defined under dynamic load case along with the mass reference load, then seismic weight is considered from dynamic load case only. For multiple dynamic load, if you specify mass model under each dynamic load, program considers only the mass model specified under first dynamic load and other mass models are ignored. A warning with the load case number from which the mass is considered is reported in the output. If multiple mass reference load cases are specified, then program internally add all loads from all these mass reference load cases and total load is used for the seismic weight. After dynamic analysis, you can find a file in the same folder with the same file name and extension mass.txt. In this file, all seismic weights or lumped masses are specified for each joint in each direction along with total mass in each direction. So if you want to check the mass used for seismic analysis, you can directly open this file and check. You can also use this as a load for other model for seismic analysis. That's all about how to define seismic mass using traditional and new approach. Final step is to add the seismic load cases. There are few rules to add static seismic loads in a model. For static seismic loads must be added to the first primary load case in the list. If load is applied in all 3 directions, then first 3 primary load case should be used to define all static seismic load cases and then other load cases should be added. Else, you will notice an error message in the output file that seismic load is not the first load case and analysis will be terminated. There are several cases when the static seismic loads should be followed by perform analysis and change command, like when these seismic loads are used in iterative analysis or factored in a repeat load case, or multiple analysis and optimization commands are assigned. All these seismic load cases should be analyzed individually and then reset the stiffness matrix using change command before analyzing next load case. A warning message is reported in the output file for this. And finally, maximum 8 static seismic load cases can be added in a model. If you add more than 8 seismic load cases, then analysis is terminated and an error message is reported in the output. This number does not include dynamic load case, so you can add 8 static seismic load cases along with multiple dynamic load cases. That is allowed. Coming to the addition of seismic load in a primary load case. In the seismic load window, you can find few options like the direction in which the earthquake load is generated, which is any of the 3 orthogonal directions. When the surface wave generates due to the earthquake, generated waves can travel in any direction, and depending on the nature of wave, it displaces the ground. Hence, fundamentally seismic force can be applied on the structure from any direction. But for structural analysis, we consider the force in 2 orthogonal directions along with vertical component of the seismic force depending on several criteria mentioned in relevant code. If the seismic force resisting elements are not parallel to this orthogonal axis, then additional load combination cases needs to be considered. The load factor is optional and by default it is considered as 1, which means seismic load is acting in the positive x or z direction with full magnitude. Now if you want to apply the load partially, you can specify multiplying factor. Also, if you want to apply the load from reverse direction, from minus x or minus z direction, then you can use negative factor. In general, we don't apply seismic load in negative direction. That is considered in the load combination where we create another set of combination cases with negative combination factor. Now there are 2 additional options: multiplying factor for accidental torsion and natural torsion. Various international building codes suggest to increase the shear force in lateral load resisting elements generated from the twisting about vertical axis of building. For diaphragms that are not flexible, the distribution of lateral forces at each level shall consider the effect of the inherent torsional moment Mt and accidental torsional moment Ma. To understand what are these and how to apply the same using the factors in load window, we need to first understand how seismic force is applied to a floor and torsion is generated. Consider this building structure. As discussed earlier, for static seismic load, base shear is calculated first and then it is distributed to each floor level. Now this lateral seismic force induced at any level acts at the center of mass of that story. Let's isolate a floor of this building to understand this. For this floor level, rigid diaphragm is assigned and depending on the mass distribution, center of mass can be calculated. Center of mass is nothing but a hypothetical point where the entire mass of an object may be assumed to be concentrated. In similar way, we can compute the center of rigidity of this floor. Center of rigidity is referred to as the stiffness centroid of a diaphragm, which is the location within a floor diaphragm at which lateral load produce only translational displacement. Depending on that location, orientation and dimension of the structural elements like the column, the shear wall, this center of rigidity can be calculated. For seismic force, the design lateral force acts at the center of mass of the diaphragm and resisting force which resists the generated seismic force acts at the center of rigidity. If the center of mass and center of rigidity is same point, then there will not be any torsion. But if these locations are different, then additional torsional moment is generated. and this needs to be considered during seismic analysis, as suggested by different codes. Now, the difference between the center of mass and center of rigidity is termed as the static eccentricity. If you specify a rigid flow diaphragm, then by default this static eccentricity is considered for the analysis, and torsion generated for this eccentricity, known as the natural or inherent torsion, is added with the generated seismic force. Now in some code, it is mentioned that this static eccentricity should be multiplied with a factor which is called the dynamic amplification factor. To specify this factor, you need to specify the natural torsional moment factor or DEC parameter. For rigid diaphragm, the default value of this factor is 1, which means natural or inherent torsion due to static eccentricity is considered for the torsion calculation. To specify the dynamic amplification factor greater than 1, you need to specify proper value in this field. If the dynamic amplification factor is greater than 1, then additional part is considered by subtracting the specified value from 1. So if you specify the factor as 1.5, then static eccentricity value will be multiplied by 0.5 to calculate the additional torsional value. Depending on what value is suggested in the relevant design code, you need to provide this factor. Note that this value should be specified as greater than 1, as any value less than 1 means you are trying to reduce the natural torsion, which is not supported. Now, there is another part of this torsion calculation, which is the accidental torsion. Till now, we have considered that the center of mass of this floor is a fixed location, which might not be true. The center of mass might be shifted to any direction, and this additional shifting of center of mass needs to be considered in the analysis. Accidental torsion is assumed to be the displacement of the center of mass each way from its actual location by a distance equal to 5% of the dimension of the structure perpendicular to the direction of the applied force. Means if you apply seismic force in x direction, then the float dimension in z-axis needs to be multiplied by a factor 0.05, and this additional torsion needs to be considered in seismic force. Note that this factor can be specified either positive or negative depending on the direction of shifting of the center of mass. The design eccentricity value is the sum of these two eccentricity values, static eccentricity from the difference of center of mass and rigidity, and accidental eccentricity. This design eccentricity is multiplied with the design lateral force at the float to calculate the torsion value. If you go through different seismic code, more or less similar equations are mentioned there. For ASCE 716 code, under clause 12.8.4.1, 2 and 3, this torsion consideration is mentioned. For accidental torsion, 5% or 0.05 times the orthogonal dimension is considered. There is no dynamic amplification factor specified here, and static eccentricity value is directly added with the accidental eccentricity value to calculate the design eccentricity. So for this case, natural torsional factor can be skipped, as by default it is considered in the analysis, or you can also specify the value as 1. Also, the accidental torsion factor needs to be specified as 0.05. For EC8 code and IS 1893 code, two equations are mentioned to calculate the design eccentricity value. In first equation, the dynamic amplification factor for static eccentricity is specified as 1.5, which means natural torsional factor should be specified as 1.5 and accidental torsion factor should be specified as 0.05. For second equation, the amplification factor is 1, so no need to specify the DEC value, or it can be specified as 1. The accidental torsion factor should be specified as minus 0.05. Now, whichever of these two equations produce more vulnerable results, that should be considered in the analysis. There is another accidental torsion option available in the seismic definition window. This is same as the accidental torsion factor in the load window, but there is no option to provide any factor. If you tick this, program calculates the accidental torsion on basis of 5% orthogonal dimension. Also, if this option is specified, the natural torsion factor will be ignored and only the accidental torsion for all seismic loads will be considered. Let's take an example how this additional torsion is calculated for seismic force from positive x direction. For this flow, say the center of mass and center of rigidity coordinates in z-axis are z1 and z2 and flow dimension in z direction is zl. If the natural torsion factor is 1.5 and accidental torsion factor is 0.05, then the dynamic eccentricity should be dc minus 1 into static eccentricity part plus 0.05 into plane dimension perpendicular to the seismic force direction, that is z-axis, which comes as 0.5 into z2 minus z1 plus 0.05 into zl. This dynamic eccentricity is multiplied with the design lateral force value at this flow level to calculate the additional moment or the torsion value. Note that if you assign rigid flow diaphragm, then center of mass is automatically calculated and reported in the output file. For each rigid diaphragm, the flow information like height and weight along with the x and z coordinate of center of mass is reported. To check the center of rigidity, you can include print dia shear command, which reports the diaphragm center of rigidity coordinates in the output file. In ASCE 716 code, an additional amplification factor to accidental torsion is mentioned under clause 12.8.4.3. If you want to consider this factor, you can calculate this manually and then multiply this with 0.05 or the accidental torsion part. This final value needs to be specified as accidental torsion factor. Now this natural torsion is only considered when you define a rigid flow diaphragm, else this part is skipped, and the reason is in ASCE 7 code it is mentioned that only for non-flexible diaphragm inherent torsion should be considered. If you model flexible diaphragm, then this part can be ignored. Also, without any rigid diaphragm, program is unable to determine the static eccentricity as center of rigidity cannot be computed. As for semi-rigid diaphragm, in-plane deformation on float points could be differing due to in-plane deformation of the slab. Now coming to the last part, which is the stiffness modeling. This is the most important part as stiffness plays a vital role for seismic analysis, and if you arrange the lateral load resisting elements properly, seismic effects can be minimized. We know for any normal beam column slab structure, gravity load transfers the slab to beam, then to column, and finally to the foundation. For lateral load like seismic load transfer path is different from this. Here, load is transferred through the lateral load resisting frame from slab to shear wall or bracing and finally to the foundation. So both diaphragm modeling and placement of shear wall and bracing is very important for any seismic efficient structure. There are several other remedies to minimize the earthquake effect like inclusion of base isolator or different types of damper like tuned mass or liquid damper. For time restraint, I cannot cover all parts of stiffness modeling. I will only cover the diaphragm modeling part. There are different types of diaphragm like flexible, rigid, semi-rigid. Some software like RAM structural system allows to define a pseudo-flexible diaphragm also. What type of diaphragm should be used in the model? That depends on several criteria. Instead, you can define a slab using plate elements and that will behave like a flexible diaphragm. There are few problems associated with the flexible diaphragm modeling where your modeling time increases to define the plates along with increased analysis time. Also, few activities like torsion check is not performed for this diaphragm as suggested in the code. To eliminate the tedious plate modeling, you can use rigid diaphragm option where modeling of slab is not required. Rather, stiffness of the slab is considered only for analysis. So you can skip plate modeling and inform program about the level where it is present. During analysis, the stiffness of diaphragm is considered. Rigid diaphragms have infinite in-plane stiffness properties and therefore they does not exhibit any membrane deformation, whereas semi-rigid diaphragms simulate actual in-plane stiffness properties and will need to be used when significant in-plane deformation does occur or when required by the code. For most RCC slab systems where the slab is sufficiently thick, the moment of inertia can be represented with cubic function of length, which is a large number. So in-plane deformation of this slab for lateral load is almost negligible, and rigid diaphragms produce results nearly identical to those of semi-rigid diaphragms. There are two options available in STAAD to create a rigid floor diaphragm. First option is using master-slave command. When you define a node as master node and other nodes as slave node, then the behavior of the slave nodes are same as the master node. The restraint direction can be assigned to any direction, plane or completely rigid where all degrees of freedom are restrained. Using this principle, all nodes of a floor can be defined as slave node with the center of mass as master node with rigid option selected as direction. This will ensure a rigid diaphragm which has no out-of-plane deformation. But one major problem of this process is to determine the center of mass manually. For any rigid diaphragm, master node must be the center of mass. I have already discussed about the reason for this. For master-slave option, this center of mass is a unknown point which needs to be computed manually. With complex floor geometry, this is a tough job. To simplify this, another option is provided which is called rigid diaphragm. Here you can specify the height of the floor or the Y range where the floor is located along with the joints or plane range, and program internally identifies the level as a floor level and selects all the joints located in the floor. Now program automatically calculates the center of mass of that floor depending on the mass model that you have created. If you use rigid diaphragm, then mass model must be defined using mass reference load case, else there will be an error and analysis will be terminated. Now if there is any existing node at the calculated center of mass, then master node is assigned at that node and rest of the floor nodes are specified as slave node. But if there is no existing node, then program creates a node at that location and assign that node as master node. In the output file, the location and node number of the master node is reported along with the floor weight for each diaphragm. In this context, just want to add another point. If there is any cutout present in the slab, like a lift core or utility passage, or multiple connected towers with central hollow core, you can duplicate this using diaphragm command. You can select the nodes, those are located on the floor slab, and ignore any node at the cutout. Then program understands that there is no diaphragm present at that zone and accordingly neglects any mass defined at the hollow zone. This is very easy as there is no need to calculate the center of mass manually and everything is automated. You only need to define the floor level. Mass model have already been created during seismic analysis and hence this can also be skipped. That's why it is always better to use mass reference load rather than traditional approach. It is used for floor diaphragm also along with the seismic weight definition. Few notes. Diaphragm should be specified from lower level to higher level in order. So specify the first floor level first and then second and so on. If you select the master joint manually for any diaphragm, then you need to select it for all diaphragms. Combination of this does not work. Better to leave it to auto calculate option where program automatically calculates the master node. Diaphragm does not work with set ZUp command. So if you plan to rotate your global axis using set ZUp command, then you cannot use this facility. You can use perform rotation command rather than using set ZUp command, which works fine to rotate the global axis system. Slope diaphragms are not supported. Only horizontal planes can be specified as diaphragms. Finally, maximum 150 number of diaphragms can be specified in a model. Well, this is a large number. Still, if you want to specify more diaphragms, you can specify that using the set rigid diaphragm option at the beginning. Another major benefit of rigid diaphragm is we can check vertical irregularities like soft story as suggested in clause 12.32 of ASCE 716 code. If a building has a floor which is 70% less stiff than the floor above it, it is considered a soft story building. This soft story creates a major weak point in an earthquake, and since soft stories are mostly associated with retail space or parking garage in the lower level of a building to accommodate large open space, so when they collapse, they can take the whole building down with them, causing serious structural damage which may render the structure totally unusable. It is necessary to eliminate this type of structural problem. Instead, check soft story command checks this problem if floor diaphragm is assigned and reports if there is any problem associated with weak story. You need to assign more lateral load resisting elements like shear wall to make the story more stiff to lateral load. Finally, about shear wall. Shear wall design has already been implemented in STAAD.Pro CONNECT Edition using STAAD.Advanced Concrete Design module. You only need to model it using parametric model option with wall option selected. This is an advanced measure which can handle complex geometry and internal density points properly. Also, you can model it using Physical Modeler, which is an advanced modeling mode. In my previous webinar with Physical Modeler, I have described the process to model and design shear wall using STAAD.Advanced Concrete Design module. That's all from me today on seismic analysis. There are several other topics related to seismic analysis which I am unable to cover today. If you want to know more about any particular topics, post that. I'll try to cover it in my future session. Hope to see you all in my next session.